Welcome to today's paper reading. Today's paper is titled LLaMA-Omni, Seamless Speech Interaction with Large Language Models. This paper was published on the AR14 preprint by Qingkai, Fang and colleagues from the Key Laboratory of Intelligent Information Processing, Institute of Computing Technology, Chinese Academy of Sciences. The abstract introduces GPT-4o, which allows for real-time interaction with large language models through speech, significantly improving user experience over traditional text-based methods. However, there is a gap in the development of speech interaction models based on open-source large language models. To address this, the authors propose LLaMA-Omni, a model architecture specifically designed for low-latency and high-quality speech interaction. LLaMA-Omni integrates a pre-trained speech encoder, a speech adapter, a large language model, and a streaming speech decoder, eliminating the need for speech transcription and enabling simultaneous text and speech response generation with very low latency. The model is built on the LLaMA 3.1-8b Instruct model and is trained using a dataset named Instructs2S200K, which includes 200,000 speech instructions and corresponding responses. Experimental results indicate that LLaMA-Omni outperforms previous models in both content and style, with a response latency of just 226 milliseconds. Additionally, the model can be trained in less than 3 days using only 4 GPUs, facilitating efficient development of speech-language models in the future. The introduction of this paper discusses the limitations of current large language models, LLMs, in supporting only text-based interactions, which restricts their applicability in scenarios where text input and output are not ideal. The emergence of GPT-4o has introduced the possibility of speech interaction with LLMs, significantly enhancing user experience. However, there is a lack of open-source models addressing this need. The simplest approach to enabling speech interaction involves a cascaded system using automatic speech recognition, ASR, and text-to-speech, TDS, models, but this method tends to have higher latency. Multimodal speech-language models have been proposed to address this, but practical challenges remain. The paper introduces LLaMA-Omni, a novel model architecture designed for low latency and high-quality interaction with LLMs. LLaMA-Omni includes a speech encoder, a speech adapter, an LLM, and a streaming speech decoder, enabling simultaneous generation of text and speech responses with extremely low latency. Figure 1 illustrates how LLaMA-Omni processes speech instructions to generate both text and speech responses simultaneously, achieving an extremely low response latency. This capability is crucial for seamless speech interaction with large language models, enhancing user experience in real-time applications. The LLaMA-Omni model architecture consists of several key components: the speech encoder, which uses the Whisper Large V3 encoder to extract meaningful representations from speech, the speech adapter, which maps these speech representations into the embedding space of the large language model, LLM, and the LLM itself, which generates text responses based on the speech input. The model employs a two-stage training strategy. In the first stage, the model is trained to generate text responses directly from speech instructions, with the speech encoder frozen and only the speech adapter and LLM being trained. In the second stage, the focus shifts to generating speech responses, with all components frozen except the speech decoder, which is trained to align the output hidden states with the discrete unit sequence using the CTC loss. Figure 2 illustrates the architecture of LLaMA-Omni, which includes a speech encoder, a speech adapter, a large language model, LLM, and a speech decoder. The left side of the figure details these components and their interactions. On the right, it shows the two-stage training strategy employed for LLaMA-Omni. The first stage focuses on training the model to generate text responses directly from speech instructions, while the second stage trains the model to generate speech responses. The speech decoder operates in a non-autoregressive manner, utilizing connectionist temporal classification, CTC, for alignment during training and inference. The construction of speech instruction data, referred to as Instructs2S200K, involves several key steps. First, instruction rewriting is performed to adapt text instructions for speech input. This includes adding filler words to simulate natural speech, converting non-text symbols into spoken forms, and ensuring the instructions are brief. Second, response generation focuses on creating concise and synthesizable responses suitable for speech interactions, avoiding complex structures that cannot be synthesized by TTS models. Finally, speech synthesis is carried out using models like Cozy Voice 300M SFT for natural-sounding instructions and DITS for standard voice responses. This process results in a dataset of 200,000 speech instruction data. In this section, we discuss the experimental setup and evaluation process. For the training data, we utilize the Instructs2 S200K dataset, which includes 200,000 speech instruction data. To extract discrete units corresponding to the target speech, we employ a pre-trained k-means quantizer that has learned 1,000 clusters from Hubert features. The pre-trained Hi-Fi-GN vocoder is used to synthesize discrete units into waveform. The model configuration involves using the encoder of Whisper Large V3 as the speech encoder and LLaMA 3.1-8B instruct as the LLM. The speech adapter performs a 5x downsampling on the speech representations. The training process follows a two-stage approach, with a cosine learning rate scheduler and a total training time of approximately 65 hours on 4 NVIDIA L40 GPUs. Table 1 presents the ChatGPT scores for the S2 TIFF and S2 SIF tasks on the Instructs2 S-Eval benchmark, along with the alignment scores between speech and text responses. The table highlights that LLaMA-Omni outperforms other models in both content and style scores for the S2 TIFF task, achieving a content score of 3.23 and a style score of 3.81. For the S2 SIF task, LLaMA-Omni also shows superior performance with a content score of 2.69 and a style score of 3.12. Additionally, LLaMA-Omni achieves the lowest ASRWER and ASRCR scores, indicating better alignment between speech and text responses. Table 2 illustrates the trade-offs between latency, speech-text alignment, and speech quality under various unit chunk sizes, omega. As the chunk size decreases, latency notably reduces, exemplified by a latency of 226 milliseconds at omega equals 10, which is lower than GPT-4o's average audio latency. However, this reduction in chunk size correlates with increased ASRWER and ASRCR, suggesting potential challenges in alignment. Conversely, increasing the chunk size improves speech quality as measured by the Atmos metric, indicating smoother and more natural speech synthesis. This data underscores the importance of balancing response speed and speech quality based on specific application needs. Table 3 presents the average decoding times for various models on S2 TIFF and S2 SIF tasks. For the S2 TIFF task, LLaMA-Omni stands out with a notably low decoding time of 1.49 seconds per instruction, significantly lower than other models. In the S2 SIF task, SpeechGPT's decoding time is approximately 25.60 seconds, reflecting its serial output process. LLaMA-Omni, however, excels by outputting both text and speech responses simultaneously, showcasing its efficiency in handling both tasks. Table 4 presents responses from various models to the instruction "How do I wrap a present neatly?" Qwen2 Audio provides a comprehensive guide with specific steps and suggestions for adding decorations. Salmon's response is more concise, detailing the process of folding and sealing the wrapping paper. In contrast, LLaMA-Omni's response highlights the importance of aligning and smoothing the paper edges for a neat finish. In the field of speech and audio language models, early research focused on training models on semantic or acoustic tokens of audio, enabling audio generation without text. Joint training of speech tokens and text has led to decoder-only models like Volley, capable of tasks such as speech recognition and synthesis. To leverage large language models, LLMs, studies have explored creating native multimodal models by adding speech tokens to the LLM's vocabulary, such as SpeechGPT, or by adding a speech encoder before the LLM, focusing on speech understanding tasks. Additionally, streaming generation methods aim to produce output before the entire input is received, crucial for tasks like simultaneous interpretation. These methods include monotonic attention, CTC-based, and transducer-based approaches, with recent research extending decoder-only LLMs to streaming generation tasks. In this paper, the authors propose LLaMA-Omni, an innovative model architecture designed for low latency and high-quality speech interaction with large language models, LLMs. The model is built upon the LLaMA 3.1-8b Instruct model and includes a speech encoder and a streaming speech decoder capable of generating both text and speech responses simultaneously. To align with speech interaction scenarios, the authors constructed the Instructions 2S200K dataset, which contains 200,000 speech instructions and corresponding responses. Experimental results indicate that LLaMA-Omni delivers superior responses in both content and style, with a response latency as low as 226 milliseconds. Additionally, training LLaMA-Omni requires less than 3 days on 4 GPUs, facilitating rapid development of speech interaction models based on the latest LLMs. Looking ahead, the authors plan to explore enhancing the expressiveness of generated speech responses and improving real-time interaction capabilities. Thank you for watching.